G'day. Let's talk about the universe's ultimate monsters. These aren't creatures from myth or legend. They're real, and they're lurking out there in the vast, dark expanse of space. I'm talking about black holes. For decades, we've seen them as cosmic prisons, points of no return where the rules of reality as we know them just completely break down. Anything that gets too close, a stray planet, a wandering star, even light itself, is pulled in by an unstoppable force of gravity. Once you cross that line, the event horizon, that's it. The man who found that crack was none other than the brilliant physicist Stephen Hawking. In the 1970s, Hawking was deep in thought, trying to unite two of the biggest ideas in physics. Einstein's general relativity, which describes the world of the very large, like stars and galaxies, and quantum mechanics, which governs the strange, fuzzy world of the very small, like atoms and particles. On a quantum level, it's a bubbling, frothing sea of virtual particles that pop into and out of existence for fleeting moments. They appear in pairs, a particle and its antiparticle, and then they usually annihilate each other almost instantly. Think of the biggest, most massive stars you can imagine, stars many times more massive than our own sun. These celestial giants live fast and die young. For millions of years, they are nuclear furnaces, fusing lighter elements into heavier ones in their cores. Eventually, the star starts to run out of fuel. The core collapses in on itself with such violence that it triggers a spectacular explosion known as a supernova. The outer layers of the star are blasted out into space, creating a beautiful expanding cloud of gas and dust. Now, let's dissect one of these cosmic beasts. The most famous feature of a black hole is its event horizon. This isn't a physical surface you could touch, like the ground on a planet. It's more of an informational boundary, a line drawn in space-time. Imagine you're in a spaceship, flying towards a black hole. As you get closer, the gravitational pull gets stronger and stronger. You'd have to fire your engines harder and harder to pull away. So, what would actually happen to you if you were unlucky enough to fall into a black hole? The scientific term for it is tidal disruption, but astronomers have a much more descriptive name for it: spaghettification. It's exactly what it sounds like. This tidal force is unbelievably powerful, capable of ripping apart not just spaceships and astronauts, but entire stars that wander too close, tearing them into streams of gas that then spiral into the black hole. Not all black holes are created equal. They come in a variety of sizes, which tells us a bit about how they formed and what their role is in the universe. The most common type we know of are the stellar mass black holes. Then you have the big ones, the real Goliaths. These are the supermassive black holes. These monsters are on another level entirely, with masses ranging from millions to billions of times the mass of our sun. Now this is where our story takes a sharp turn into the wonderfully weird world of quantum mechanics. On the tiniest subatomic scales, the vacuum is a chaotic and buzzing hive of activity. It's a place where pairs of virtual particles are constantly popping into existence from literally nothing. But Hawking wondered, what happens if a pair of these virtual particles pops into existence right on the edge of a black hole's event horizon? This is where the magic happens. You see, there's no such thing as a free lunch in the universe. The law of conservation of energy is absolute. The escaping particle becomes real, carrying its energy with it. So, where does that energy come from? The universe has to balance its books. This faint glow is what we now call Hawking radiation. It was a shocking, revolutionary discovery. Stephen Hawking's calculations showed for the first time that black holes are not completely black. So, if black holes are constantly radiating away their mass, does that mean they will eventually disappear? The answer is a resounding yes. But don't hold your breath waiting to see it happen. The evaporation of a stellar mass black hole would take around 10 to the power of 67 years. That's a 1 followed by 67 zeros. Imagine a giant block of ice, the size of a mountain, sitting in a room that is just a fraction of a degree warmer than freezing. The ice will melt, but it will do so incredibly slowly. This is like a supermassive black hole in our current universe. The evaporation of a black hole isn't a steady linear process. It's a runaway reaction that starts incredibly slowly, but ends with spectacular violence. This is because the rate of Hawking radiation depends entirely on the black hole's mass. As the black hole slowly loses mass over countless eons, its temperature begins to rise. The gentle simmer starts to turn into a noticeable boil. By the time it has shrunk to the mass of a car, it is an object of unimaginable energy, spewing out high-energy particles and gamma rays in all directions. The slow drip has become a fire hose. We now arrive at the grand finale, the very last moments of the black hole's existence. After eons of slow evaporation, the black hole has shrunk to a mass of around 228 metric tons, roughly the mass of a blue whale. At this point, everything changes. The black hole has entered the final second of its life, and it's going to go out with a bang that will echo through the empty cosmos. In these last moments, the black hole's temperature skyrockets to billions, then trillions of degrees. It becomes hotter than the core of any star that has ever existed. The final flash would be predominantly in the form of high-energy gamma rays, the most energetic form of light. It would be a brief but supremely powerful beacon, momentarily outshining everything else in its galactic neighborhood. After the final, brilliant flash of energy fades away, what is left? The most straightforward answer, at least according to the simplest version of Hawking's theory, is absolutely nothing. The curvature in space-time that it once created, that deep gravitational well, would just flatten out. The event horizon would vanish, and space-time would heal itself, leaving no scar behind. But, this simple answer leaves us with that deep, nagging problem we touched on earlier. The information paradox. What happened to all the information about everything that fell into the black hole? It would be like burning a book and discovering that the smoke and ash contained no trace of the words that were written on its pages. Hawking's discovery did more than just give black holes a finite lifespan. It fundamentally changed our understanding of the laws of physics and the nature of the universe. Ultimately, the discovery of Hawking radiation transformed black holes from being simple cosmic dead ends into being the most fascinating theoretical laboratories in the universe. They are the places where our most successful theories break down, forcing us to search for a new, deeper understanding of reality. So, where does this journey leave us? We started with the idea of black holes as eternal, unchanging monsters, the universe's ultimate prisons. This revelation, born from the genius of Stephen Hawking, doesn't just change our view of black holes, it changes our entire perspective on the cosmos. This story forces us to think on scales that are almost impossible to grasp. The lifetime of a black hole makes the 13.8 billion-year history of our universe seem like a fleeting moment. Learning about the life and death of black holes also gives us a profound sense of connection to the universe's grand cycles. The matter that makes up our world, our bodies, was forged inside stars. As we stand at the end of this exploration, we are left with more questions than answers, and that is the true sign of a great scientific mystery. The evaporation of black holes, while providing a stunning theoretical framework, has opened up a whole new Pandora's box of puzzles that push the very limits of our knowledge. What really happens in that final explosive second? Our theories give us a glimpse, a prediction of a massive burst of energy, but the truth is we don't really know. If the holographic principle is correct, are we living in a cosmic hologram? Is the three-dimensional reality we experience merely a projection of information stored on a two-dimensional surface at the edge of the universe? The story of black holes, from their discovery as theoretical oddities to their transformation into evaporating information-scrambling puzzles, is a perfect illustration of the scientific process. It reminds us that the universe is far stranger, more complex, and more wonderful than we can possibly imagine. Every time we think we have a handle on it, it throws us a curveball like Hawking radiation. So the next time you look up at the night sky, remember what's out there. Not just the beautiful twinkling stars, but also the silent, invisible monsters that are their ghosts. And in their final moments, in their predicted death, they illuminate the path forward for our own understanding, reminding us that the greatest adventure is the quest for knowledge itself, a journey that, like the universe, is constantly evolving, with new wonders waiting just over the horizon.